Section 8.2, starting with number 3. In the intro video, we looked at the most basic of rational functions. That was y equals 1 over x. And its graph looked like this. And we talked about the different parts, the vertical asymptote, the horizontal asymptote. Those are big deals. And just the shape of it. This curve here being the mirror image of this curve over here. So we're gonna, as we do every time we learn about graphing functions, we're going to start to change things and see how that looks compared to what we call the parent function. Right. This is the parent function. You can see where the vertical and horizontal asymptotes are, and we'll see how those change when we change stuff about the function. So this function is going to be 3 over x instead of 1 over x. So how is that going to change things? Well, in this function here, if we made a table of values, we could put in 1, and 1 over 1 would be 1. We could put in 2, 1 over 2 would be 1/2. We could put in 3, 1 over 3 would be 1/3. So let's see how things change for this function. Let's set up a table of values. And 3 divided by 1 will be 3. 3 divided by 2 will be 3/2. And 3 divided by 3 will be 1. Okay. So you can see how for this function, when x was 1, y was 1. For this function, when x is 1, y is 3. And when x is 2 for this function, y is 1/2. And when x is 2 over here, y is 3/2. And when x is 3 here, y is 1/3. And here, when x is 3, y is 1. So you may notice all of these values are 3 times bigger than these values when compared to the same x values. So let's graph those points. If x is 1, then y is 3. If x is 2, then y is 3/2. It's 1.5. And when x is 3, then y comes down here to 1. So we can see the shape that we're going to make. We talked about the vertical asymptote of 1 over x. It's at 0 at x equals 0, because if you put 0 in for x, that you've got a problem. You can't divide by 0. And we get the same problem here. If you put a 0 in for x, you still are trying to divide by 0. So the vertical asymptote is still there. And the horizontal asymptote apparently is still at y equals 0. Still comes down and approaches the x-axis. And that kind of makes sense, because the only thing that's changed is that this number up here is a 3 instead of a 1. Which you could look at this way, 3 times 1 over x. Right? This is the same thing. These two things are equivalent. Here you have the original function 1 over x, and you just multiply it by 3. So it just makes all the y values 3 times bigger than they were in this graph here. And this will just be the mirror image. Right? So we'd have -1, -3, -2, -3/2, -3, -1. Just the mirror image. And let's just let's put 1 over x on here. We got 1, 1, 2 and 1/2, 3 and 1/3. So that original graph, the parent function, is 1 over x. It looks like this. So this green one just is kind of taller than this original function of y equals 1 over x. Okay, so you can see how, and you could reason through how if you put a different number up here, and that's how you changed, it would just kind of, make it taller. Or if this were a fraction, or if this were a decimal up here, that was less than 1, then you'd have 1 over x times some small number that would make it come even lower than this blue function here. We'll see that in a second. Let's go to number 5. Just scroll down here. There you go. This one's going to be y equals negative 5 over x. Right. So remembering what the graph of 1 over x looks like this. And it has points at 1, 1, and 2 and 1/2, and so on. So what's this function going to look like? Keeping in mind the same idea that we used in the previous problem. How about if we just say negative 5 times 1 over x? Right? So it looks very similar to the 3 over x, except for it's negative. This 5 is going to take all the values that you would get for 1 over x and multiply them by 5, so it's going to get, it's going to be taller, just like the last one was. So if we set up a table of values here, we put in a 1, 2, and a 3. Let's go to 5 even. Okay. So we're going to multiply 1 over x by negative 5. So, or we could look at it as taking negative 5 over x, or whichever way we like to do it. So we'll put a 1 in here. That's 1 over 1 times negative 5. That's going to be negative 5. Put a 2 in there. 1 over 2. That's 1/2 times negative 5. That's negative 5 halves. Put a 3 in there. You get negative 5 thirds. Then negative 5 fourths. Then negative 5 fifths, which is negative 1. So what we got in this function when we put in a 1 was a positive 1, and then we got a positive 1/2, positive 1/3. Now these guys are negative. So let's see what kind of a effect that has on this graph. So 1 comma negative 5, that's a little bit small. There we go. So 3, 4, 5, negative, or 1, negative 5. So instead of being up here, it's down here, and let's see what continues to happen. 5 halves, negative 5 halves. So that's negative 2 1/2. And negative 5 thirds. Let's see, 4, 5 thirds. And negative 5 fourths. So that's like right there. And negative 1 should be just right there. So you see how it's slowly coming up close to the x-axis again, just like it had done in the graph of 1 over x and 3 over x we just did. Okay, that should be pretty curvy. Okay. Now the rest of the graph, we could think it should be the mirror image, but since this is kind of weird, let's think about that for a second. Well, if it were just 5 over x, then we would have this curve being over here, right? If it was positive 5 over x. Just like for positive 3 over x, we had this other curve down here. But it isn't positive 5 over x, it's negative 5 over x. And all those values that would have been negative y values, right? We would put in negative values for x and get negative values here. Those get multiplied by a negative 5, and now they're positive. So indeed, that is a confirmation that we still have that mirror image of the other part of the graph. Okay. So there we go. This is the same as 1 over x, except for it's now what was up here is now down here, and what was down over here is now up here. And so we could say that it's flipped vertically. And we could say it's taller, if that's a word you like, or I don't know what description you'd like to use, stretched out vertically, or whatever that describes the change in the look of this graph compared to 1 over x. Alright, now let's do number 7. Y equals 0.1 over x. Okay, so very similar. It's just the number that's up here in the numerator has changed. We could again look at it as 0.1 times 1 over x. So we have the 1 over x, just like always, times 0.1. So what's that 0.1 going to do? Well, where 3 and negative 5 made this into a bigger value, the 0.1 is going to make it into a smaller value. Let's set up a table of values. So when we put in 1, we have 1 over 1, that's 1, times 0.1, that's just 0.1. Put in 2, 1 over 2 times 0.1, so that's 1/2 times 0.1, or 0.5 times 0.1. So that's going to be 0.05. Yeah, and then put in a 3, you get 0.1 times 1/3. And so that would be 0.033, and so on, repeating. And just so that we see what's going on, let's just compare that to the table of values we would get with 1 over x. It'd be xy. This little cloud here is for remembering things. We remember that the table of values for 1 over x, so for y equals 1 over x, we got 1, 1/2, and 1/3, or 1, 0.5, and 0.33, repeating. You see how these values have become 10 times smaller than these values were. The decimal places moved to the left 1 for each of these. So each one has been divided by 10. So when we go to graph this, let's look at these values. Let's graph the 1 over x function. So it goes through 1, 1, 2 and 1/2, 3 and 1/3. Let's even make this bigger because we don't want to be able to see this. Scale this up. So 1, 1, 2 and 1/2, 3 and 1/3. So this graph's going to look something like this, and then we'll get the mirror image over here. This one, though, 0.1 over x, we get 1 and 0.1, 1 and 1/10. That's very small. Let's see, 2 and 0.05, that's even half of that. 3 and 0.0333, that's 1/30th. It's tiny. Okay, it's hard to even draw this very accurately because it's such small values. But we can see that the graph would go through here, and there, then come up like this, and do a similar thing along the y-axis. And over here we will get the mirror image. So having a smaller number on top now has made this graph shorter. Say it's shorter than y equals 1 over x. That makes sense because we're taking what's virtually the original function and multiplying by 0.1. Multiplying things by 0.1 makes them smaller. So we're going to get smaller values for this function. And so that makes sense that it would be a shorter graph. Let's do number 11. Y equals 4 over x. Okay, there's a little bit more. Let's just think about this for right now. 4 over x, what's that going to do to the graph, this 4? We should look back to the previous 3 problems that we've done and recognize that this is like 4 times 1 over x, and so we're just going to get larger values. It's going to be like stretched out. It's going to be a taller graph than the 1 over x graph. Okay, but after that, we add 3. So what's that going to do? let's look at it. Let's look at how this changes the 1 over x graph. So we're going to just take 4 times 1 over x. So we're going to get the 1 over x, that's the parent function, multiply it by 4, that's what makes it taller. Okay, so we're going to get these bigger values. There's 4 times, or values that are 4 times bigger than the values of the 1 over x graph. And then we're going to add 3. Okay, so we're going to get these values that are multiplied by 4 and then add 3. Think about what that might do to the graph. And while you're thinking about that, we'll set up this table of values. So let's go 1 to 4. So we get 1 in here. We get 1 over 1, that's 1 times 4, that's 4. 1 times 4 is 4. Then we're going to add 3 to that, and that's going to be 7. Okay. And then we're going to put 2 in here. You get 4 times 1/2, that's 2. Plus 3, that's 5. And then we're going to put a 3 in there. 4 times 3 is 4/3. 4 times 1/3 is 4/3. Plus 3, let's see, that's 4/3 and 3. So this would be 1 1/3 plus 3, so that's 4 1/3. Put a 4 in there. 4 times 1/4 is 1 plus 3. And that gives you a 3. Let's see, 4 times, no, it's going to be a 4. Excuse me. Okay. So let's think, what if we kept putting bigger and bigger values in here? What if we put in 1,000 or something like that, or 4,000? What's going to happen? Well, think about what happened to the parent function, 1 over x. We put really big values in here. Then this 1 divided by a really, really big number is going to be a really, really small number, right? And we're going to take this really, really small number and multiply it by 4. Well, a small enough number multiplied by 4, that's still going to be really small. If we had a decimal and then 1,000 zeros and a 1, and you multiply it by 4, that'd be just a decimal point, 1,000 zeros and a 4, not much bigger. Then we're going to add 3, so it's going to be 3.1,000 zeros and a 4. That's not very big. It's not very much bigger than 3. So it looks like where all the other graphs have been coming down and getting closer to the x-axis, close to the x-axis, close to the x-axis. This one doesn't get close to the x-axis. It doesn't get close to 0. It just gets closer to 3. Right? We're taking 3 and we're adding on, as x gets really big, we're adding on a tiny, tiny number. All right, so let's stop talking in the theoretical, and let's graph this and see what it looks like. Okay. So let's put in these values, 1, 7. 1, 7. Then 2, 5. 3, 4 and a third. 1, 2, 3, 4 and a third. And we put in 4. We go up to 4. 1, 2, 3, 4. Okay, and if we keep on putting in values, they're going to get just closer and closer and closer to 3. That's what we were just talking about. So let's just put a dotted line here at 3 to show how that is the number we're getting close to. We'll never get below that, right? By going further out for x, we're just going to put a bigger number in here for x, which this will get really small, never quite to 0. Right? And multiplying by 4 is not going to make much of a difference when it's so small. And then we're going to add that tiny, tiny number to 3. So we're just going to keep on adding tiny, tiny numbers to 3 and just being slightly above 3 forever and ever. So our graph will go through all these points and just get really, really close to 3. Okay, and if we put some values over here, we would find for -1, -2, and so on, that we would again get large negative values here as we got x close to 0. And then as we went to the left and put big negative values in for x, we would still be getting really close to 3, only we'd be just slightly smaller than 3. Okay. Because we'd be doing the exact same thing, only we'd be taking that small amount off of 3. We'd be subtracting it from 3 because it would be negative. Okay. So let's see the full directions here. We graphed the function. And let's think about how it looks compared to 1 over x. It is almost exactly the same except for it's taller because of that 4 there. And it's moved up 3. So we could say vertical shift up 3. Okay. Now, something else that they want us to include are the domain and range. That's some fancy words. Domain would just be all the inputs. How can we express all the things that we can put into the inputs, put into the function? We can put anything into this function except for 0, right? Because think about it. What can we divide 1 by? Absolutely anything we want to, as long as we don't divide by 0. The only no-no in division is dividing by 0. So we could just say all real numbers except 0. You could also say shorter than that. This is a symbol with this double vertical line here and then an R. This means all real numbers. And then we could just say x does not equal 0. Right. So that's a shorter way to say the exact same thing. All real numbers such that x does not equal 0. The range, if the domain is all the inputs, the range is all outputs. Okay. What values can the function have? What values can you have for y? Well, it looks like anything. It can go on forever in the negative direction, forever in the positive direction. All these values are possible. The only one that you can never actually achieve is positive 3. So we have all real numbers except 3. X can't be 3. Or sorry, y can't be 3. Okay, so that's the domain and the range. Next, we'll do number 14. F of x, that's just our function notation. 1 over x plus 2. Oh, that's interesting. So, let's just do our normal table of values. 1, 2, 3. We'll put in a 1. It'll be 1 over 1 plus 2. That's 1 over 3, so 1/3. Put in a 2. 1 over 2 plus 2. That's 1 over 4. And then we get 1 over 5. Okay, that's interesting. That's a little different. What about 0? Let's put in a 0. Is that, before we couldn't put in a 0 for x because that would mean dividing by 0. But when we put in a 0 for x in this function, does that mean dividing by 0? No, it means dividing by 2. So we just get 1/2. So now this graph's going to look different, when you go to graph it. You're not going to have that vertical line telling you that you can't put a 0 into the function. That's not the shape this is going to have. So, but, maybe there is some other value still that you could put in that you would wind up dividing by 0. Is there something you put in for x that would make you be trying to divide by 0? How about -2? We put a -2 in there. -2 plus 2 is 0. We're dividing by 0. That's undefined. You can't divide by 0. So instead of 0, it's -2 that you can't put into the function because -2 would cause the denominator to be 0. So we just kind of shift that, what would have been at 0, we shift that vertical asymptote over to -2 because that's the problem now. Okay. And it looks like we're not adding or subtracting anything on afterward over here. So there's not going to be any vertical shift. So we're still going to have a horizontal asymptote here at 0, right? No matter how big we put a number in for x, all that's going to happen is we're going to get closer and closer and closer to 0 without ever actually getting to 0. So let's plot some of these points, or all these points. 0 and 1/2, 1 and 1/3, 2 and 1/4, 3 1/5. They just keep getting closer and closer to 0, and we'll continue to do that forever. So let's connect all these points without it looking too terrible. And we'll get the mirror image right over here. So we get a very similar graph to what we've been getting, only now it's shifted to the left. You could say shifted left 2. Now we want the domain and range. So the domain, what are all the inputs? What can we put in for x, or maybe what can we not put in for x? Everything works. We can see by the graph everything works. At all values of x, you can find the graph. You could find a point for the y. All places except for -2. That's where we have that vertical asymptote. That's saying this x value is off limits. So x cannot be equal to -2. Okay. Otherwise, we could have all real numbers, just as long as x is not equal to -2. How about the range? What values can we get for y? It looks like absolutely anything except for, again, we're just approaching 0. So all real numbers work for the range, except y will never be equal to 0. So there's your range. Okay. Next, we'll do number 15. Y equals -5/x. We've actually done that problem. We graphed -5/x for number 5. But then we're going to subtract 7. Okay. So this is like -5 times 1/x minus 7. So we're going to have the same kind of values here as we did for 1/x. And we're going to multiply by -5. That's going to make the graph flip over, and it's going to make the graph taller. And then we're going to subtract 7, which means we're going to shift down 7. So we'll do, let's say, 3, 4, and 5. So 1/3 times -5 is -5/3 minus 7. Let's see. So -5/3 is -1 2/3. Minus 7 is -8 2/3. Put on a 4, we have -5/4. -5/4 is -1 1/4. Minus 7 is -8 1/4. Put a 5 in there. 1 divided by 5 is 1. -5 times 1 is -1. Minus 7 is -8. Okay. So let's look at a graph of this function. 1, 2, 3, and -8 2/3. That's going to be something like right there. 4, -8 1/4. So just slightly above that previous point. 5 and -8, so that's just going to be right on right there. Okay. And so as before, if we kept going on and on and on for x, try putting in a big number for x, get out your calculator, throw it in there, see what happens. We'll put in a big number for x, that's going to make this a small number, and then multiplying it by -5, all that's going to do is the 5 is not going to make it that much bigger. It's still going to be a really small number, but it'll be negative. And we'll subtract that really small negative number from -7, so we'll get numbers that are slightly below -7. Right? So that's just going to be kind of this cap at -7. That's going to be what they're going to keep getting close to, but never quite get there, because we're just going to keep subtracting these tiny, tiny numbers off of -7. That's just not going to be that much of a change, and so that's just going to be close to -7. Then we get the mirror image over here, just like that. And yeah, so there's the graph. What's the domain? The domain, all the values that you can put in for x. Well, we'll start to see here a pattern, or should see a pattern here. Nothing in the denominator is any different than the original function 1 over x. So the only thing you can't put in for x is 0, because that would make the denominator 0. So any number will do, any real number, except x cannot be 0. How about the range? Y is going to take on all values except for it will never quite be -7. Okay. Yes, that was number 15. Now number 27. This will be the last one. Y equals x plus 4 over x minus 3. So this seems to kind of come out of nowhere. And where did the x come from in this numerator here? Well, let me show you. I'll just kind of come over here and do a little work over to the side. Let's say we did 3 over x, and we wanted to add 4. So this is not something that we're unfamiliar with. 3 over x plus 4. This 3 would make it 3 times taller, and this 4 would shift it up 4. So, but what if we wanted to write this as a single fraction? What would we need here in order to add the 4 to the 3 over x? What we would need is a common denominator, as with any time you want to add fractions. We would need a denominator of x. We need them to be the same, but we can't just put that. We have to multiply the numerator and denominator by the same thing. So 4x over x. You could think these x's cancel out, and so that's the same as 4. So now what we have is 4x plus 3 over x. So you can see how we could wind up with an x in the numerator. You could just imagine we had an original function of, it would look more something like this, 1 over x minus 3 plus something else. And then you would need a common denominator of x minus 3 and so on. So we won't go into detail on that. But that's where this comes from. So this is basically the same as something that was originally 1 over x minus 3, and then we were adding on some number here. So we could expect that we'll get some kind of a change in the denominator here, and then maybe we'll have a vertical shift as well. So in order to graph this, we're going to use what I'm about to show you in future sections, graphing more involved rational functions. This is the most basic. The first thing we can look at is what can we not put in to the denominator? The only thing we can't put in the denominator is what would make the denominator 0. So what makes the denominator 0 is a positive 3. And where we find that value that cannot go in for x, that's where we're going to find our vertical asymptote. So we can just throw our vertical asymptote on there. Okay. And then we could find our horizontal asymptote. And remember that horizontal asymptote, that's the value that the graph approaches but never quite gets to. So let's think about what number this fraction would approach if we keep putting really big numbers in for x. Okay, so let's put in 100 for x. We put in 100 for x, we get 104 over 97. 104 over 97. Let's just throw that in a calculator. Okay, so 104, turn it on, 104 divided by 97. It's a little bit bigger than 1. Okay, let's put 1,000 in there. If we put 1,000, we get 1,004 over 997. Let's try that one. 1,004 divided by 997. Okay, very similar looking number, only it's closer to 1. Let's try putting in 1,000,000. Okay, let's go really big. 1,000,004. And then, yeah, and then we'll get, what, 999,997. So 1,000,004 divided by 999,997. Okay, even closer to 0. Just the tiniest bit off of 0. This 0.000007 is just a tiny number. So it's just slightly bigger than 1. So as we put in really big numbers for x, we're just getting closer and closer to 1. So that is going to be our horizontal asymptote. And we're going to talk about this in so much more detail in the next section. But this is a good intro. And we could put in x values and all that kind of stuff and plot points, and that would be absolutely fantastic. One thing that we could do, we pretty much see what's going to go on here. We're going to have a shape, there's no negatives in front of it, either of the x's, so we're not going to get a flipped over graph. It's going to be normal. It's going to be up here and down here. Let's just give ourselves one point somewhere that'll give us an idea of kind of how tall to make this graph. A real easy one would be to find the X Intercept. The X Intercept will be wherever this x plus 4 over x minus 3 is equal to 0. Let's multiply both sides by x minus 3. And we get x plus 4 equals 0. Right? Because 0 times x minus 3 is 0. I think I cancel that on this side. And that makes sense because if wherever this function is equal to 0, that just be where the numerator is equal to 0. If the numerator is equal to 0, whatever you're dividing by, it's still going to be 0. So where x is -4, this function is going to be 0. That's where you're going to find an X Intercept. So -1, 2, 3, 4. That's your X Intercept. So you know that this graph is going to come along the line y equals 1 until we get to here. It's going to cross over a little bit. And then we'll just draw the mirror image over here. Okay. So this, having it look like this, a little bit different than what we're used to. As we move on, all of our functions are going to look like this. It's just going to be one fraction, not adding anything on to the end here, just one fraction like that. And we're going to do a very similar thing, looking at the vertical and horizontal asymptotes, plotting some points, and finding x-intercepts and so on. Okay, well, I hope that was helpful. Thanks for watching.